Introduction to ring signatures. Welcome to the channel. Please consider subscribing. I produce videos daily, covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. Today, we will explore a fascinating and powerful cryptographic tool designed for anonymity, the ring signature. Imagine a situation where a message needs to be authenticated by a member of a specific group, but the identity of the actual person who signed it must remain hidden from the public. This is precisely the problem that ring signatures solve. A standard digital signature proves authorship, saying, "I, Alice, wrote this message." A ring signature, by contrast, makes a different claim. It says, "One of us from this group wrote this message," without revealing who the one is. The diagram on the slide provides a simple analogy. A group of executives signs a document, but instead of individual signatures, there is only a single, authoritative stamp. You know the approval came from a legitimate executive, but you don't know which one. This provides both authenticity and anonymity. In this presentation, we'll break down the properties of ring signatures, the clever mathematics that make them work, and their powerful real-world applications. Recap. Standard digital signatures. Before we dive into the specifics of ring signatures, let's quickly recap what a standard digital signature does. A signature scheme like ECDSA or Schnorr creates an undeniable, one-to-one link between a single person and a single message. When Alice signs a message with her private key, she produces a signature that can only be verified with her corresponding public key. As the diagram illustrates, this provides two crucial security properties. The first is authenticity. The verifier knows the message definitely came from Alice. The second is non-repudiation. Alice cannot later deny that she signed the message, as only her private key could have created that specific signature. This is fantastic for accountability. However, this absolute link to a single identity is a feature, not a bug. In situations where the signer needs to remain anonymous while still proving the authenticity of their message, this one-to-one link is a significant problem. This limitation is the very reason ring signatures were invented. The need for anonymity. To truly appreciate ring signatures, we need to understand the limitations of a standard digital signature. A normal signature, like one made with Schnorr or ECDSA, creates an undeniable link between a person's identity, their public key, and a message. This is excellent for accountability and non-repudiation. But what about situations where accountability needs to be at the group level, while the individual needs protection? Consider a whistleblower inside a large corporation. They want to leak a document and prove that it came from an authentic internal source, but revealing their identity would lead to severe repercussions. Or think of an anonymous cabinet member wanting to confirm a government policy to a journalist. A standard signature is not an option. This is where ring signatures shine. The signer can create a ring of potential signers by gathering the public keys of other members of their group, for example, other employees or cabinet members. They can then sign the message on behalf of this entire ring. The resulting signature proves the message's origin from within the group, but makes it impossible for an outsider to pinpoint the actual signer. It provides a perfect blend of credibility and plausible deniability. Introducing ring signatures. Hiding in a crowd. A ring signature provides a cryptographic equivalent of hiding in a crowd. It allows a signer to prove they are part of a group without revealing their specific identity. The signer, who we will call the true signer, selects other participants to form an anonymous set, which we call the ring. This ring is composed of the public keys of all chosen participants, including the true signer's public key. Then, using their unique private key, the true signer generates a signature that appears to be from the entire group. When a verifier checks the signature, the verifier can confirm with certainty that one of the public keys in the ring corresponds to the private key that signed the message. However, the verifier has absolutely no way of knowing which one. As far as any observer is concerned, every member of the ring has an equal probability of being the true signer. This provides a powerful form of plausible deniability for the signer. Core properties of ring signatures. For a ring signature scheme to be effective, it must satisfy three core cryptographic properties. First is correctness. This is the basic guarantee that a signature honestly generated by a true member of the ring will always be accepted as valid by an honest verifier. The system has to work reliably. Second is unforgeability. This property ensures that it is computationally infeasible for anyone who is not a member of the ring to create a valid signature for that ring. An outsider, even if they have all the public keys of the ring members, cannot forge a signature that will pass verification. This guarantees the authenticity of the message. The third, and most important, property is signer ambiguity, also known as anonymity. This guarantees that if a verifier is given a valid ring signature, they have no way of determining which specific member of the ring actually produced it. To the verifier, every single member of the ring is an equally probable candidate for being the true signer. These three properties together create a system that is secure, authentic, and private. Spontaneity and non-cooperation. One of the most powerful and defining features of a ring signature is its spontaneity. The creation of the ring is entirely a one-sided affair, managed solely by the true signer. This is a crucial distinction from other group-based cryptographic schemes. To create a signature, the signer does not need permission, consent, or even the awareness of the other individuals whose public keys they are including in the ring. They can simply gather the publicly available keys of their colleagues, their managers, or any other group they wish to be associated with, and include them in the signature calculation. This ad hoc and non-cooperative nature is what makes ring signatures so powerful for use cases like whistleblowing. The other members of the ring are completely uninvolved and, in fact, are protected by the same plausible deniability as the true signer, as it's impossible to prove they didn't sign the message either. This contrasts sharply with group signatures or multi-signatures, which require formal setup and cooperation among participants. The mathematical setup. To understand how a ring signature is constructed, we first need to define our mathematical components, which are standard in modern cryptography. We will be working within an elliptic curve group, which is chosen for its high security and efficiency. Everyone using the system agrees on a set of public parameters. This includes a specific elliptic curve, a public generator point G on that curve, and the prime order of the group, Q. We also need a cryptographic hash function, H, which can take any input and produce a random-looking number. In this system, every user I has a secret private key, which is a scalar number x sub I, and a public key, which is the point p sub I on the curve, calculated as x sub I times g. The security of this entire setup relies on the elliptic curve discrete logarithm problem. The fact that it's easy to calculate p sub I from x sub I, but computationally infeasible to go in the reverse direction and calculate x sub I from p sub I. These are the same fundamental building blocks that power many other cryptographic systems, including Schnorr signatures. The intuition. A cryptographic loop. Before we get lost in the formulas, let's build a high-level intuition for how a ring signature works. The core idea is to create a closed cryptographic loop, or a ring of dependencies. The signature is constructed in such a way that each person's part of the signature depends on the person before them. As a verifier, you can follow this chain of dependencies from one person to the next around the entire ring. The math is designed so that if you start at the beginning and follow the chain all the way around, you should end up exactly where you started. The magic trick is that only a person who knows one of the secret private keys can perfectly close the loop. An outsider trying to forge a signature can create a chain, but when they get to the end, there will be a mathematical gap they cannot bridge. They won't be able to make the end of the chain connect back to the beginning. So, when a verifier checks the signature and finds that the loop is perfectly closed, they know that one of the members of the ring, who possessed a valid private key, must have been the one to create it. Worked example. Setup. To make this concrete, let's walk through a full example with simplified values. Imagine a ring with 3 members: Alice, Bob, and Carol. Their public keys are P1, P2, and P3. Let's say Alice is the true signer, so her position in the ring is S equals 1. The message she wants to sign is the quick brown fox. Our signature will consist of a starting challenge E1 and 3 responses: S1, S2, and S3. Alice's goal is to produce these values so that a verifier can confirm the signature is valid. For this example, we will represent our hash outputs and responses as simple text for clarity, but in a real system, these would be large numbers derived from elliptic curve operations. Alice knows her private key X1, but she does not know the private keys for Bob or Carol. Example: commitment. Alice's first step is to make her secret commitment. She generates a secret random nonce, which in a real system is a large number, but for example, let's just call it K. She uses this nonce to compute her public commitment point. R equals K times G. Let's imagine this point R can be represented by the text commitment point R. Now she is ready to start building the ring, beginning with the person after her, Bob, who is at position 2. Example part 2. Building the fake links. Alice now needs to create the parts of the ring for the non-signers, Bob and Carol. She starts with Bob at index 2. Since she doesn't know his private key, she must fake his response. She picks a random number for his response, S2. For our example, let's say she picks the value random response S2. Now, she needs to compute the challenge for the next person, Carol. She uses the formula E3 equals H of M, S2 times G minus E2 times P2. To do this, she needs E2. Where does that come from? The signer has to work backwards from their own commitment. Alice starts her loop right after her own position. She computes the first real challenge, E2, by hashing the message and her commitment point R. So, E2 equals H of the quick brown fox. Commitment point R. Let's say this hash output is challenge hash E2. Now she can compute the next link. She calculates E3 by hashing the message, her fake response S2, the challenge E2, and Bob's public key P2. Let's say the result is E3 equals challenge hash E3. She has now completed the link for Bob. Example part 3. Closing the loop. Alice has built the chain up to Carol and has the challenge for Carol's position, E3. She repeats the process for Carol. She picks another random response, S3, let's call it random response S3. She then uses this to compute the challenge for the next person in the ring. The next person after Carol is Alice herself, at position 1. So, she computes E1 equals H of M, S3 times G minus E3 times P3. Let's say this hash result is E1 equals challenge hash E1. Now comes the magic step. She has the challenge E1 that corresponds to her own position. She must now compute her own response, S1, not randomly, but using the special formula that requires her secrets. S1 equals K minus E1 times X1. This specific calculation ensures that her response, when checked by a verifier, will correctly produce the challenge E2 that she started the chain with. She has used her private key X1 and her secret nonce K to perfectly close the cryptographic loop. Example: the final signature. Alice has now computed all the necessary components. She has the starting challenge, E1, and all 3 responses, her specially crafted S1, and the random S2 and S3 for Bob and Carol. She bundles these together to form the final signature. The signature is the pair of the starting challenge and the list of responses. For our example, the signature would be the value challenge hash underscore E1 and the list of strings calculated underscore S1, random response underscore S2, random response underscore S3. She can now publish the message along with this signature and the list of public keys P1, P2, P3 that form the ring. Example: the verification process. Now, a verifier receives the message, the ring of public keys P1, P2, P3, and the signature we just created. The verifier's job is to confirm that the loop is closed. They do not know that Alice is the signer. They start with the E1 from the signature. Using S1 and P1, they compute their own version of the next challenge, E2. Then, using this E2, S2, and P2, they compute E3. Finally, using E3, S3, and P3, they compute their version of the first challenge, E1. Because Alice used her private key to calculate S1 precisely, the verifier's calculation of E2 will yield the exact same value as the E2 Alice used to start her chain. This consistency will propagate through the entire loop. When the verifier computes their final E1, it will be identical to the challenge hash E1 they started with. The loop is closed, and the signature is proven valid. The verifier is convinced a member of the ring signed the message, but because S2 and S3 are indistinguishable from random numbers, they have no idea who it was. A problem. Linkability. The ring signature we've described provides perfect, unconditional anonymity. If the same person signs two different messages using two different rings, there is absolutely no way to tell that the signatures came from the same author. This is ideal for a whistleblower who wants complete deniability. However, this total unlinkability is a disaster for applications like anonymous electronic cash or secure e-voting. In those systems, you need to ensure that a person can only spend their money once or cast their vote once. If you can't link their actions, they could double spend or vote multiple times without being caught. This is known as the double spending problem. To solve this, we need to intentionally introduce a specific, limited form of linkability into our otherwise anonymous signature scheme. We need a way to tell if two signatures came from the same person, without revealing who that person is. The solution. Key images. The clever solution to the linkability problem is a cryptographic tool called a key image. A key image acts as a unique identifier for a signer's private key, but in a way that is computationally dissociated from their public key. The formula to create a key image is I equal operator x sub s times h sub p of p sub s. Let's break this down. X sub s is the signer's secret private key. P sub s is their public key. H sub p is a special type of hash function that takes a point on the curve, the public key, and hashes it to another point on the curve. By multiplying this hashed point by their private key, the signer creates a new point, I, the key image. This key image has two crucial properties. First, for a given private key, it is completely deterministic. The same private key will always produce the same key image. Second, it is computationally infeasible to link a key image back to the public key it was derived from. You can't tell which public key in the ring corresponds to a given key image. To use this, the signer is required to publish the key image along with their ring signature. How key images prevent double spending. Now that we have the key image, how does it prevent double spending? The process is quite simple, as the diagram on the slide illustrates. When a user wants to perform an anonymous action, like casting a vote or spending a coin, they create a valid ring signature as before. In addition, they must also compute and include the unique key image derived from their private key. When a verifier, such as a blockchain node or a voting server, receives this transaction, they perform two checks. First, they verify the ring signature itself to ensure that the transaction is authentic and came from a valid member of the ring. If that passes, they perform a second check. They take the key image provided with the signature and look it up in a database that contains all the key images that have been used in the past. If the key image is not in the database, it means this is the first time this user has performed this action. The signature is accepted, and the new key image is added to the database. However, if the key image is already found in the database, it is a clear indication that this user is attempting to act a second time. The transaction is immediately rejected as a double spend attempt. This provides the necessary security without compromising the anonymity of the signer's identity. Ring signatures versus group signatures. It's important to distinguish ring signatures from another concept called group signatures, as they solve similar but distinct problems. The biggest difference is the lack of a manager. In a ring signature scheme, there is no setup and no central authority. Any user can spontaneously decide to form a ring with any other set of public keys and create a signature. The anonymity is unconditional and cannot be revoked. A group signature, on the other hand, is a more formal arrangement. There is a designated group manager who is responsible for adding members to the group. This manager holds a special master key. While signatures from the group are anonymous to the public, the group manager has the power to open a signature and reveal the identity of the original signer if there is a dispute or a need for an investigation. As the table on the slide summarizes, you would choose a ring signature for unconditional, ad hoc anonymity, and a group signature when you need managed, revocable anonymity. Ring signatures are for plausible deniability, while group signatures are for managed accountability. Application Deep Dive. Monero. The most famous and successful real-world application of linkable ring signatures is the privacy-focused cryptocurrency, Monero. Monero was designed from the ground up to provide strong anonymity for its users, and ring signatures are the core technology used to obscure the sender of a transaction. When you send Monero, your wallet automatically and randomly selects a number of other recent transaction outputs from the blockchain to act as decoys. It then creates a ring signature that includes the public keys associated with these decoys alongside your own. The diagram on the slide shows this concept. Your true transaction output is hidden among a crowd of other plausible outputs. Anyone looking at the blockchain can verify that the transaction is valid, meaning real money was spent, but they cannot tell which of the outputs in the ring was the one that was actually spent. The mandatory inclusion of a key image with every transaction ensures that you cannot spend the same output twice. This combination of ring signatures for sender ambiguity and key images for double spend protection is what gives Monero its strong privacy guarantees. Other applications. Beyond cryptocurrencies, the unique properties of ring signatures make them perfectly suited for a variety of other high-stakes applications where privacy is paramount. One of the most cited examples is anonymous whistleblowing. An insider at a company or government agency can use a ring signature to leak a document. They can form a ring with the public keys of their fellow executives or officials. The signature proves that the leak came from a legitimate source with high-level access, lending it credibility, but it protects the ID of the individual who took the risk. Another powerful use case is in secure e-voting systems. Ring signatures can be used to construct a system where each voter can prove they are on the official list of registered voters and thus have the right to cast one ballot without revealing who they are. This allows the system to accept only valid ballots while keeping the link between a voter and their actual vote completely secret, which is a cornerstone of any free and fair election. Finally, they can be used for issuing official statements with collective responsibility. Imagine a corporate board or a council of judges issuing a sensitive statement. A ring signature allows them to prove the statement came from their group without attributing it to any single individual. Advantages and disadvantages. Like any technology, ring signatures come with a set of trade-offs. Their primary advantage is, of course, anonymity and privacy. They provide a strong, mathematically guaranteed way to obscure a signer's identity within a group. Another key benefit is their spontaneity. There is no need for a group manager, complex setup ceremonies, or cooperation from other ring members, which makes them incredibly flexible. However, they are not without their disadvantages. The most significant one is signature size. A ring signature includes data for every single member of the ring, so its size grows linearly with the number of people you add. A larger ring provides better anonymity but comes at the cost of more data. The verification process is also more computationally intensive than for a standard signature, as the verifier has to perform calculations for every member of the ring. Finally, the total anonymity can be a downside in scenarios where accountability is needed. Because the anonymity is unconditional, there is no way to unmask a signer, even if they abuse the system. This makes them unsuitable for systems where a trusted third party might need to resolve disputes. Summary and conclusion. Today we've unraveled the clever cryptography behind ring signatures. We've seen that they provide a unique form of digital signature that offers group-level authenticity while preserving the anonymity of the individual signer. Their security is rooted in the three core properties of correctness, unforgeability, and, most importantly, signer ambiguity. We explored the elegant mathematical loop that a signer's private key creates and that a verifier checks. We also learned how this pure anonymity can be optionally modified with key images to create linkable signatures that prevent double spending in systems like Monero. By allowing any user to spontaneously create an anonymous group on the fly, ring signatures provide a powerful and flexible tool for privacy in a world where digital accountability and personal protection are often in conflict. Thank you for your attendance. Please consider subscribing to the channel.